Okay, this one is called a slotted, excuse me, a slotted disc. It's a disc spinning around that has a notch or a slot in it, in which is sliding a little piece of metal or plastic called a slider that has on it point B, the point of interest. We can call this either A or either O or A. There you go. Okay. And the question is, now let me just say, I'm not going to, well, let me put them down here. The numerical values play a role, but frankly, they're not too critical. Okay, if you can read that, I hope. And let me just tell you what the goal is. Okay, so what we have here is a disc like the Frisbee. Only imagine it has a slot milled out of it, in which is sliding this little critter, and we're going to mark this point B, the point of interest. The whole thing has both an angular velocity and an angular acceleration. So we're getting up into the worst case scenarios, all right? It's not going to get a lot worse than this. And again, because the way the problem is laid out, they're telling you that what is known is the radial distance from the center, A, the radial distance of point B, and that's called R. They not only know what R is, but they know what its derivatives are. Okay, yeah, Marion?
Is that point 1 or point 4?
I'm sorry?
For R, is that point 1 or point 4?
This one here. Oh, I'm sorry. Oh yeah, that's absolutely point 4.
Okay, and then
R double dot, that is the European one, okay, 0.15. All right, thank you. 0.15. I love that. I spent a summer in Europe. I was fascinated by that one.
Are we looking for VB and AB, or are we looking for the...
I'm sorry, your question is, what are we looking for?
Yeah, are we looking for VB or the swap?
Oh, thank you. How astute. See, you could have just called out 0 and we'd be done. Yeah, thank you. That's exactly right. Nice catch. Okay, we are interested in the linear velocity and the linear acceleration of point B. All right. Okay, so this is getting a little more ragged here. So I'm going to let you guys participate a little bit more. How about you, sir, in the white shirt right there?
Me?
Yeah, what's your name?
Natsum?
Nasu. Is it? No.
Natsum.
Natsu.
Yeah.
Natsu.
Natsum. It's like a knot, and then if you want something.
Okay, is it not some?
Yeah. There you go.
What was the question I was going to ask you? Yeah, Natsum. What would you do first if you encountered this on the printed page? This is a problem on your problem set. Where do you begin? What is this whole conversation about?
It's how to begin, or it's about how to begin. So I'd start with setting up like a mini local coordinate system.
It's about the artful use of intermediate frames, also known as body coordinate systems. Yeah, that's exactly what he said. So if you had to choose a body coordinate system, you're going to attach a coordinate system to the body, where would you put it?
I would Do the little x from like the point to B, and then the j perpendicular to it.
Very good, very good. What Natsum is saying is if it was up to him, he'd make this the body coordinate system. He'd have the little I hat go out along the slot and the j go perpendicular to that. Natsum, how come you chose that?
I just
I'm
figured
saying
it'd be-
you're right. It was smart. I'm just saying why.
I mean, you'll be able to choose the point B along the I hat direction.
Yeah, and look what you were given.
That's awesome. Yeah, I didn't
All
know.
right, and this, everybody hear what he says? That's awesome. And this is, and on many levels, this is the point, all right, of the intermediate frames. What intermediate frames or body coordinate systems allow you to do is set up the problem in a way to enable you to exploit the information you're given. This is what you know. This is what you know. This is what you're given. So choose a coordinate system where that's right there. All right. And so since he's done that, what that gives us, look at all this. Okay, that's a cheapie. Anybody could have done that. Same here. But watch this. Here comes R. How about it? Natsum? You chose it.
Yeah, you 0.4 in. the-
Well, yeah, okay, let's not do that. Yeah, no numbers yet. Let's do this. Yeah, and this is, now we're in the level of area of strategy. This is a message from me to you when you're working, both when you're working problems on problem sets and on quizzes. Defer the use of numbers for as long as possible. All right? Stay with the symbols. The symbols just, anyway, push the symbols as the symbolic answer as far as you can. Ideally, you get all the way to the end and just plug the numbers in at the last, because once you start throwing around decimal points and digits, it just, anyway, it's a mess. Okay, so if that's the case, Natsum, what's this?
It's going to be R dot in the I hat direction.
Same deal. Okay, all right, piece of cake. So now let's okay, Natsum, we're going to go for, let's go for the easy one first. I remember this formula by now. You just write that from memory, right? Okay, so let's start knocking them down. Take these terms out of here.
So we can knock out VA
Knock out VA. And how do you get away with that?
because that's where you're starting your local coordinates.
You've chosen the local coordinate system's origin to be at the point of pivot, right? How about VREL? We just blew that off.
No, we don't blow it off.
Okay, very good. Cannot blow this off because
It's a very important.
it's
like,
not
thing
zero. It's not zero.
within the local coordinate system.
Precisely. The point in question is in fact moving in the local coordinate system. You just said so, right? Okay, so, and if I may, now, just for a good measure, I will put these numbers in just so you can see. To give you some means of checking. And over here, I'm going to draw the silly thing. Okay. All right, everybody see that? Everybody got it? You can see that it's going to have two components, and here they are. A component each in the Y and J direction. All right, and now let's do the other one real quick. And once again, I'm just going to okay, Nonson. Can you start throwing these out for me? This is supposed to be a cross in there. Say
So
again?
the acceleration of A is 0.
Okay.
The last term at the end, the acceleration relative, is not 0.
It's not 0.
R double dot,
Yeah.
I hat.
You got to keep it.
VREL, we went over that already. It's just going to be R dot.
All right, that's very good. Let me show you here are the pieces. Okay, how about helping me label these? This is point B. This is direction I. This is direction J. And in the interest of time, I'm going to kind of short circuit this. So what's this one? Why did I draw this in this direction? Which one is
That's
that?
negative omega squared R.
Exactly, that's this guy here. Okay, and now you can take your choice. One of these is one and one is the other. Doesn't really matter.
2 omega for the one.
Yeah, exactly. One of these is alpha cross R, AB. One of these is the Eulerian. It's in that direction. And the other is the Coriolis. All right, now I'll just draw the answer here so you can track this down at your leisure. Okay. And that is the end of video segment 4.4. Any questions on this? Yes, ma'am, or wait a minute. Nico.
Yes. So I'm confused as to why the centrifugal acceleration is negative. I understand from the formula the negative sign popping up.
Oh, excuse me a second. Hang on a second. Say that again. What was your concern?
So my concern is the fact that there's nothing resisting motion in the positive I-hat direction. So therefore, the centripetal acceleration, even though I know it is towards the center, it's causing motion in the positive I-hat direction, as far as I can tell physically, because the block is sliding outwards due to the lack of centripetal force. If that makes any sense. So, I mean...
Yeah, let me see if I can repeat your question. Okay, your concern is this acceleration component itself. You said a couple of things. One is, this is of concern to you, the centripetal component, because you were concerned about its sign, and the other was a little more subtle. It had to do with, you wanted to know what was causing this, what kept it from flying out.
Well, I mean, I think isn't the principle of the problem is that it's flying out?
Indeed.
Yeah.
Right. Well, let me simply say, I think the point of confusion here, your point is well taken. What I should have said, I put this up here a little quickly. What I should have said is that by some undisclosed external means, this point B was being driven, was being pushed, was being positioned with respect, down the slot with respect to the origin, according to this, at this instant.
Okay, so it's being held at a fixed point.
It's being held, but not at a fixed point. Okay, what I didn't say is, there's some external agent here, whether it's a bar or a person or some other object. I'm just saying, somebody's coming here, the voice of God is coming down, R dot and R theta, or R double dot. I'm telling you, physical system, this point B is going to move down this slot at this rate. I'm establishing its position, its velocity, and its acceleration along that slot is being established by something you're not told what it is. Does that make sense? And and so what this question really is saying is that if point B is in fact propagating down that slot thusly, where the slot is on a disk that's both rotating and accelerating, what's the acceleration of point B?
Okay. Now, just so I can clarify my understanding, if there was no set parameters for how the block was moving and it was purely in a slot that was rotating, would the sign of the centripetal acceleration switch because it was accelerating outwards at that rate?
The issue of the sign of the centripetal acceleration is a completely separate matter from, separate matter. I would say it this way: because I have told you this, and this, because I have told you these, you have enough information to know this and this. That is to say, because I told you the angular velocity, the angular acceleration, the linear position, velocity, and acceleration down the slot, I've told you enough to enable you to compute both the linear velocity of point B and the linear acceleration of point B. All right, and so that's kind of statement number one. I think you may be being a little confused by this, this term right here. Let me just point out that what this term is actually is this. That is to say, it flows from that successive differentiation of position that gives, this gives you the linear velocity, and then this is that. So if you go through the math of this, if RAB is in the direction of I, then the centripetal component will always be directed toward the center, hence the name, centripetal. If that's helpful. Okay, Nico, you want to, another question?
I think I could clarify this. I think, is the confusion arising because you think it's loosely held and by virtue of spinning it's being flung out?
That's the principle that I'm operating
Yeah,
under.
so what I think is different in the physical case would be that imagine that there's a really strong friction and it naturally would not be flung out.
Yeah.
But somehow someone has like started to push it out. And the centripetal acceleration is negative because it's slowing down. It wants to stop being flung out.
If I may add to that, once again, it is the fact that the problem specifies the angular velocity, acceleration, and these three positions here enables you to compute the acceleration of that point. If those weren't given, you couldn't do that. Yeah, Kim?
I think where his head is going to is, now that you know this velocities and acceleration, you can say F equals ma. You could compute the external hand of God in here to make it do what it's doing. You could now calculate the forces required to make it behave that way. And there are definitely some forces required to do that.
Okay.
Yeah, that's absolutely true. We haven't shown them, we haven't said what they are, but they're there.
So we need my candy.
Exactly.
There's a totally different problem is if there were no friction and it could just do its thing, those numbers couldn't possibly be those numbers. It would be something else.
Everybody got that? Okay, front row, your name, please. Michael, your question.
For these problems, is it advisable to just differentiate instead of trying to
Say that again. I think your question was, is it better to simply differentiate? Kim, I'd ask for your input. I would say not.
My answer to you is memorize that acceleration formula. You're going to need it again and again and again, and pretty soon it just becomes easy to do. And if you try to derive the answer every time, it'll take you forever.
It takes you forever. And I want to point out the risk of sounding like a broken record. The whole point of the use of intermediate frames is that they make the problem much, much simpler. What you want to do is that you want to choose a body coordinate system that enables you to easily exploit the information you're given about the problem.